And today, we're plunging right into the heart of reality itself, looking at this incredibly tiny number.
Almost infinitesimally small.
Yeah, but it shapes everything, our whole universe.
Mm-hmm.
It kind of defines the texture of what we even perceive as real, like the fundamental pixel size of existence.
That's a great analogy. And that number is Planck's constant, symbol h.
Okay.
And its value, well, since the 2019 redefinition of SI units, it's exactly 6.6260715 times 10 to the minus 34 Joule-seconds.
Joule-seconds. That unit, it's called action, right?
Exactly, action. It's basically the amount of energy used over a certain time. Think of it like a fundamental unit of effort. Or change, maybe.
Okay.
And h isn't just any unit of this action. It's the absolute smallest indivisible chunk of it that can exist.
Right. So the fact that h isn't zero, that's the whole reason we have quantum mechanics.
Not much, yeah. If h was zero, which is what classical physics kind of implicitly assumed.
Then what? No quantum weirdness.
None. Photons would have zero energy. Particles wouldn't act like waves. There'd be no uncertainty principle. Everything would be smooth, continuous, predictable.
A completely different universe.
Totally different. So h, this tiny non-zero value, it forces reality to be grainy, pixelated, like you said.
Yeah.
It introduces these discrete steps.
Okay, so our mission today is to trace where this h came from.
Exactly. We'll follow its journey from, Max Planck introducing it almost reluctantly, thinking it was just a mathematical fix,
Right.
to where it is now. A cornerstone of physics, and even how we define our basic units of measurement.
Now, we've got some great sources for this analysis of the constant itself, its role in physics, metrology. Should be fascinating.
Definitely.
So let's dive in. Where does the story start? Late 19th century.
Yep. Late 1800s physics. There was this puzzle everyone was trying to solve. How hot objects give off light.
Like that glowing iron poker analogy.
Exactly. Specifically, they were looking at an ideal version called a black body. That's something that absorbs all light hitting it and emits light just based on its temperature. Perfect absorber, perfect emitter.
And experiments, especially in Berlin around the 1890s, they showed patterns, right?
Right. Hotter objects radiated more total energy, obviously. And the peak color, the most intense wavelength, shifted towards shorter, bluer light as it got hotter. That was Wien's law. It described that shift pretty well.
But there was a snag, a big one.
A huge one. Classical physics, when applied to this black body radiation, just fell apart completely.
This is the ultraviolet catastrophe.
That's the term, yeah. Coined by Paul Ehrenfest a bit later, in 1911. Classical theory, using things like the Rayleigh-Jeans law, predicted that a black body should emit infinite energy.
Infinite. How?
Well, it predicted more and more energy at shorter and shorter wavelengths into the ultraviolet and beyond. Infinitely much energy, theoretically. Which is, obviously wrong.
Yeah, things don't glow with infinite energy. That seems like a pretty fundamental problem.
It was a crisis, a clear sign that something was deeply wrong with their understanding of physics.
So enter Max Planck. And he wasn't exactly a revolutionary. Was he more of a traditionalist?
Very much so. He deeply believed in classical physics. But then new experiments came out in October 1900.
Ah, okay.
And they showed that Wien's law, which worked okay at high frequencies, actually failed at low frequencies. So now neither of the existing formulas worked perfectly across the board.
So Planck was stuck. He needed a formula that fit all the data.
Right. And he actually found one pretty quickly, empirically, just sort of cooked up an equation that matched the experimental results perfectly.
But just having a formula wasn't enough for him.
No, for Planck, a physicist needed to derive it from first principles, and that's where the act of desperation, as he called it, came in.
Okay.
To make the math work, to derive his successful formula, he had to make this radical assumption. He had to assume energy wasn't exchanged continuously, but only in discrete packets, quanta.
He was forced into it by the math.
Pretty much. He found that the energy E of each packet had to be proportional to the frequency of the radiation and the constant linking them. That was his new constant, E high.
But he didn't think it was real, physically real.
Not initially, no. He thought it was just a mathematical trick, a formal assumption needed to get the right answer. He wasn't proposing a new physics, just trying to explain the data.
But it worked incredibly well.
Amazingly well. And when he calculated H based on the experimental data back then,
It got a value, right?
yeah, around 6.55 times 10 to the minus 34 Joule-seconds.
Which is really close to today's value.
Within about 1.2%. It's stunning. This mathematical fix turned out to be one of the most fundamental constants of nature.
Wow. Okay, so Planck introduces H almost by accident. to solve this one problem. But it didn't stay confined to black bodies, did it?
Oh, not at all. That was just the beginning. The constants started showing up everywhere, solving other mysteries.
Like Einstein and the photoelectric effect. That was pretty soon after, 1905.
Exactly. That was a huge step. Classical physics, thinking of light purely as a wave, couldn't explain the photoelectric effect properly.
Remind us what the problems were there.
Okay, so 3 main things. First, for any given metal, light below a certain specific frequency wouldn't knock any electrons out, no matter how bright the light was.
The threshold frequency.
Right. Second, the energy of the electrons that did get knocked out depended only on the light's frequency, its color, not its brightness. Brighter light just knocked out more electrons, not faster ones.
Okay.
And third, the electrons came out instantly. No delay, even for very dim light, which wave theory predicted there should be.
So how did Einstein solve this using H?
He took Planck's idea of energy quanta literally. He proposed that light itself is made of these discrete particles, these packets of energy photons.
Ah, so not just the energy exchange, but light is packets.
Exactly. And each photon carries an energy E equals E, Planck's formula. When a photon hits an electron in the metal, it's all or nothing.
The photon gives all its energy to one electron.
Yep.
Huh.
Some of that energy is used to just free the electron from the metal. That's the work function.
Like an exit fee?
Kind of, yeah. And whatever energy is left over becomes the electron's kinetic energy, how fast it moves. So, K max, higher.
And that explains everything.
Perfectly. The threshold frequency, that's just the frequency where high equals the work function.
Yeah.
Any less energy, the electron can't pay the fee.
Got it.
Why doesn't intensity matter for energy? Because intensity just means more photons, each still having the same high energy. So you get more electrons, but not more energetic ones. And the instant emission.
Right.
A single photon collision is immediate.
Okay, that's elegant. So H is fundamental to light itself. What about matter? Atoms.
Right. The next big leap, Niels Bohr, 1913. Classical physics had a huge problem with atoms, too.
They should be unstable.
Exactly. An electron orbiting a nucleus, according to classical electromagnetism, should radiate energy continuously, spiral inwards, and the atom should collapse in a fraction of a second.
Which clearly they don't.
Right, so Bohr made another radical jump, inspired by Planck. He proposed that an electron's angular momentum was quantized.
Not just energy, but angular momentum, too.
Yes. He said it could only take on discrete values, integer multiples of, well, h divided by 2.
Ah, this is where E bar comes in.
Precisely, AH bar. So angular momentum L equals n, where n is just an integer 1, 2, 3, and so on.
And what did that do for the atom?
It meant electrons could only exist in specific stable orbits with specific energy levels. They couldn't just be anywhere.
Okay, so stable orbits and the light emission.
Bohr said electrons could jump between these allowed orbits, these energy levels. When an electron jumps from a higher energy level to a lower one, it emits a photon.
And the photon's energy.
Is exactly the difference in energy between the two levels. E eq, initial E final, and since E is I for the photon.
E eq, the energy difference dictates the frequency, the color of the light.
Bingo! And this perfectly explained the discrete emission lines scientists saw when they looked at light from elements like hydrogen. Each line corresponds to a specific electron jump. They're like atomic fingerprints.
Wow. So H is structuring the atom itself.
Okay.
And then there's de Broglie.
Louis de Broglie, 1924. He took it even further. If light waves can act like particles, photons...
Maybe particles can act like waves?
Exactly. He proposed this symmetry applied to all matter. Any particle with momentum p should have an associated wavelength that.
And how does H fit in?
It's the bridge. The relation is incredibly simple.
Wavelength equals Planck's constant divided by momentum.
Yep. H connects the particle property, momentum, to the wavelength for everything.
Was that just theory, or is it confirmed?
Confirmed beautifully in 1927 by Davison and Germer. They actually showed electrons diffracting off a crystal just like waves would.
Electrons acting like waves.
Yeah.
Mind blown. Okay, so H started as a fix for light from hot things, became key to light itself, then atoms, then all matter. It really is woven into the fabric of reality.
Absolutely. And not just conceptually, but baked right into the mathematical language of quantum mechanics.
Right, let's talk about that. How does H or H bar show up in the core equations?
Well, first, H bar itself, H2 poo, it just pops up everywhere in quantum equations, often because things in physics involve circles or rotations, and 2 is related to cycles versus radians. So using age often makes equations look a bit tidier, like EEO instead of E high when using angular frequency.
So it's partly convenience.
Partly, but it's deeper than that. In the more advanced formulations, like using operators, fundamentally connects physical quantities like energy and momentum to the mathematical operations that represent them. It's really embedded in the structure.
Okay. And then there's maybe the most famous consequence, the uncertainty principle.
Heisenberg, 1927. Yeah, this is profound. It states there's a fundamental limit to how precisely you can know pairs of certain properties at the same time. The classic example is position and momentum.
You can't know both perfectly.
Never. The more precisely you know the position, the less precisely you can possibly know the momentum, and vice versa. And the limit to this trade-off is set by h bar. The relationship is auxable to.
Greater than or equal to h bar over 2. So h bar sets the minimum amount of uncertainty.
Exactly. It's not about bad measurement tools. It's intrinsic to nature. It comes right out of the wave-particle duality that H itself establishes. It's a fundamental fuzziness.
Okay, that's fundamental. And the core equation that describes how quantum systems evolve. Schrödinger's equation.
Right. Schrödinger, 1926. This is like the ESMA of quantum mechanics, but for waves. It describes how the state of a quantum system, its wave function, changes over time.
And h bar is in there too.
Front and center. The time-dependent Schrödinger equation is IJAM. That links the energy of the system, represented by the Hamiltonian operator, to how quickly its wave function oscillates or changes in time.
So it connects energy and time evolution.
Yes, and it also relates momentum to how the wave function curves or varies in space. It's basically the engine driving the quantum evolution, with setting the scale and the relationships.
So h isn't just a number in the equations. It's almost like the grammar of the equations, defining the relationships.
That's a good way to think about it. It sets the rules of the quantum game.
Okay, let's shift now to the modern day. How is Planck's constant used, practically and theoretically, right now?
Its importance has only grown, really. On the practical side, the biggest recent story is the redefinition of the kilogram.
Right, this happened in 2019.
Correct. For over 100 years, the kilogram was defined by this specific lump of platinum-iridium alloy kept in a vault near Paris.
The International Prototype Kilogram, or IPK.
That's the one. But the problem is, physical objects can change. They can gain or lose tiny amounts of mass over time, even if kept carefully. So scientists wanted a definition based on a fundamental constant of nature, something truly unchanging.
And they chose h. Why h?
Because experimental techniques had become precise enough to link h to mass very accurately, the main tool was something called a Kibble balance.
Formerly the Watt balance.
Yes. It's an incredibly clever device. It basically weighs a test mass against an electromagnetic force. By measuring electrical quantities very precisely, voltage and current, which can themselves be linked to H via quantum effects like the Josephson effect and quantum Hall effect, you can determine the mass in terms of H.
So you're measuring h by weighing something.
Initially, yes. Laboratories around the world did these incredibly precise measurements, getting values for H consistent down to parts per billion. For instance, NIST in the US achieved about 13 parts per billion uncertainty.
Wow.
And once everyone agreed on the value, they flipped it around.
How so?
Instead of using the kilogram to measure H, they fixed the numerical value of H to be exactly 6.6260715 half-10 Joule-seconds. And now that fixed value of H defines what a kilogram is.
So the definition is no longer a physical thing, but this fundamental number.
Exactly. The definition is now realized through experiments like the Kibble balance. It's a much more stable and universal foundation for mass. Took effect May 20th, 2019.
So the constant that started as a fudge factor for black bodies now literally defines how we weigh things. That's quite a journey.
It really is.
And beyond measurements, you mentioned h points to the frontiers of physics, quantum gravity.
Yes. This involves Planck units. Max Planck himself realized you could combine h with two other fundamental constants, c, the speed of light from relativity, and g, Newton's gravitational constant, to create a natural set of units.
Natural meaning not based on human conventions like meters or seconds.
Exactly. Units derived purely from the fundamental constants of the universe. We get things like the Planck length, which is incredibly tiny, about 10 meters, and Planck time, around 10 seconds.
Unimaginably small scales.
Absolutely. And the significance is this. At these Planck scales, the effects of quantum mechanics, governed by h, are expected to become just as strong as the effects of gravity gravity, governed by G and C.
So quantum theory and general relativity meet, or collide.
Collide is probably more accurate because our current theories break down there. General relativity doesn't include quantum effects, and quantum mechanics doesn't properly include gravity.
So we need a new theory.
We need a theory of quantum gravity, something that unifies them. String theory and loop quantum gravity are candidates. These Planck scales, defined by H, C, and G, represent the energy and distance scales where this unified theory would be essential.
Like conditions in the very early universe?
Exactly, right after the Big Bang. So H isn't just defining the quantum world we experience and measure, it's also pointing toward the absolute limits of our current knowledge, the realm where quantum effects and gravity become inseparable, and where the ultimate nature of space-time might be revealed.
It really defines the boundary between the known and the unknown.
In a very real sense, yes.
So bringing this all together, it's quite a story for one little constant.
It really is. From that act of desperation trying to explain glowing objects,
To becoming the fundamental unit of action, forcing reality to be discrete, quantized.
right, and the bridge in wave-particle duality, connecting momentum and wavelength for everything.
Plus, through h-bar, setting the absolute limit on what we can even know simultaneously, that inherent uncertainty.
It's woven through all of quantum theory.
And today, it's incredibly practical. It's literally how we define the kilogram, anchoring our measurements.
While at the same time, it's deeply theoretical, pointing us to the Planck scale, the edge of known physics, where quantum mechanics meets gravity.
It governs so much: the color of stars, why atoms don't collapse, the behavior of electrons, all the way to the structure of space-time itself.
It's amazing how this one tiny number, 6.626 times 10 to the minus 34, underpins so much of existence.
It makes you wonder, what if that number was just slightly different? How completely different would our reality be?
That's a profound thought to end on. The universe really does hang on these fundamental constants.